In my structural engineering made simple series, today I talk about lateral load distribution to brace frames, shear walls, and moment frames. Please take a moment and read the disclaimer at the bottom of this slide before we continue. Structures are designed to resist against lateral loads such as wind and earthquake using one of several lateral load resisting systems. These are frames with braces, shear walls, concrete cores, and moment frames. A lateral load resisting system may be solely made up of one kind of system or a combination of these four systems. The total lateral load is distributed among frames or shear walls according to their relative rigidities or lateral stiffnesses at each floor level. This video in the Structural Engineering Made Simple series presents the procedure for computing the lateral load distribution to lateral load resisting systems. Also, the procedure in computing the rigidity of shear walls, moment, and brace frames is discussed. Please note that this video focuses on the analysis only and does not cover any design procedure for lateral loads. Throughout the video, the term lateral load resisting element or simply element is used. These terms are in reference to either a moment frame, a shear wall, or a brace frame. Viewers are encouraged to consult with the ASC 7 document or the International Building Code IBC for information on how to compute the lateral force on buildings from wind and seismic effects and other analysis design requirements for lateral load resisting systems in buildings. Center of rigidity. The center of rigidity, CR, for a structure is a point at which the resultant of all rigidities pass through. It means that if the lateral load is applied at the center of rigidity, no torsional moment develops. In this video, we designate the location of the center of rigidity with respect to a reference set of axes, usually taken at the geometrical center of the floor, with YR and XR respectively. Center of mass. The inertial forces at each floor are applied to the center of mass or center of gravity, designated by Cm or Cg. Generally, most of the mass is concentrated at floor level and comprises of the floor dead weight. When weight of walls are present, 1/2 of the height of the wall below and 1/2 above the floor are considered when estimating the mass of the floor. In this video, we designate the location of the center of mass with respect to the reference axis, usually the geometrical center of the floor, with Y bar and X bar respectively. Computing the location of center of rigidity and center of mass. The center of rigidity is computed based on the relative rigidities and geometry of the structure in its plan. Let's designate Rxi as the rigidity of the ith lateral load resisting element, for example a moment or brace frame or shear wall, which is parallel to the x-axis, and let's designate Ryi as rigidity of the ith lateral load resisting element, which is parallel to the y-axis. We select a set of reference axes to identify the location of the individual lateral load resisting elements. Usually the reference axes are selected at the geometrical center of the structural floor plan. A lateral load resisting element I, which is parallel to the x-axis, is located at yi from the x-axis. However, a lateral load resisting element I, which is parallel to the y-axis, is located at a distance xi from the y-axis. Eccentricity. The center of rigidity and center of mass usually don't coincide. therefore causing an eccentricity and a torsional moment to develop. The eccentricity in the y direction is y bar minus yr. Theoretical eccentricity is shown with EY in that direction. In the x direction, the theoretical eccentricity Ex is x bar minus xr. Please note that the parameters x bar, xr, ex, etc. may be negative. Accidental eccentricity. Because of uncertainty in computing the center of mass and the center of rigidity, a certain minimum eccentricity will need to be considered and added to the eccentricity computed. This is called the accidental eccentricity and is taken about 5% of the largest dimension perpendicular to the direction of the load. Please consult with the pertinent code about the accidental eccentricity and the current recommendation on the percentage to be used. This figure shows a plan of a steel structure. Several brace frames are marked on the figure with the location with respect to the x and y axis. For example, when you look at the north frame, the middle bay is braced and has a rigidity Rx1. The distance to the reference point is y1, which in this case we use a positive value for y1. On the south frame, we have another brace frame, rigidity is Rx2, and in this case the distance would be negative y2 from our reference point. And when you look at the y direction, we also have several brace frames with different rigidities and the corresponding distances designated as x1, x2, and x3, etc. The location of the center of rigidity, again measured with respect to geometrical center of the floor, is defined by yr and xr and obtained according to these two equations. As you can look closely at these equations, you find similarities between these equations and finding a center of mass in statics. Yr is sum of the rigidities multiplied by the corresponding distances divided by the total rigidities, and x bar similarly obtained. What we do is that we look at individual elements and find their distances to our reference lines. Also notice that since our reference point is geometrical center, the distances xi and yi will be negative if the element is to the left or below this center. It is important to keep this negative sign in the equations so we would not make any mistakes in computing yr and xr. The location of the center of mass is defined by y bar and x bar and obtained in a very similar equations. We divide the entire area into different segments, and each segment has a weight called W. So Wi is the weight of segment I, which could be a wall or floor. Each segment is multiplied by the corresponding distance from the reference line and divided by the total weight. And again, these equations are equations that you have seen in statics for finding the center of mass or center of an area. Y prime I and X prime I are the locations of location of segment I from the reference point. And please notice that since our reference point is the geometrical center, the distances x prime I and y prime I will be negative if the center of the segment is to the left or below this center. I'll demonstrate this through an example. In situation when the weight distribution, including the weights of the walls, is symmetric with respect to both axes, the center of mass coincides with the geometrical center of the floor plan. Similarly, when all lateral load-resisting elements have symmetrical rigidities, the location of the center of mass will coincide with the geometrical center of the floor. In the next slide, we demonstrate the situation when the rigidities are not symmetric with respect to x and y axis, and how the center of rigidity will be different from the center of mass and the geometrical center of the floor plan. As indicated earlier, this will result in an eccentricity and a torsional moment. The effect of the torsional moment will be an additional shear force in some lateral load resisting element, as will be demonstrated in an example later in this video. This figure shows an unsymmetric rigidity configuration. For the analysis in the x direction, the lateral force is Fx, as you can see in here, and the eccentricity is Ey. This is a theoretical eccentricity, as you can see here. However, for computing the torsional moment, we use the eccentricity E prime y, which is Ey plus the accidental eccentricity we talked about, 5% of the dimension B, which is perpendicular to the direction of the load. Therefore, the torsional moment to be considered is Tx, which is Fx multiplied by E prime y. Distribution of lateral load to lateral force resisting elements. Let's look at applied force in the x direction. The applied total lateral load, in other words Fx, is distributed as shear forces to individual elements. For an element I, the total shear Vxi has two components. Vxi is Vxiv and Vxit. Vxiv is a shear force resulting from direct effect of the force Fx, while Vxit is a shear force resulting from the torsional moment Tx. Now these are the equations. The direct shear is obtained based on the relative rigidities. For example, for element I, it is the rigidity of element I divided by the total rigidity multiplied by the total force. However, for the torsional effect, we use this equation. Now, if you look at this equation closely, this is very similar to mc over I equation. It's rigidity multiplied by the corresponding distance divided by sum of the rigidities multiplied by the corresponding square of distances. In the denominator, this sigma needs to be obtained for all elements in the floor plan. And I call this one the rigidity inertia. Then once you compute this ratio, you multiply by the torsional moment Tx, and that gives you the extra shear in that element I. However, there is something very important. Per design codes, in the direction of the applied force, the torsional effect cannot be deducted from the direct shear effect. What does it mean? That means if this term is negative or zero, we have to use it as zero. The distribution of shear forces resulting from the applied load Fx is shown in here. Notice that the effect of the force Fx applying at the center of mass is the same as applying the force at the center of rigidity, but including the torsional moment Tx, as you can see here. We have brought the force and put it at the center of rigidity, and then we put the moment in there. As you can see, on the north part, the north frame, we have a force Vx1. On the south, we have Vx2. And then there are also some additional shear forces developed in those frames or lateral resisting elements which are parallel to the y-axis, and I'm going to talk about this next. The load in the x direction also creates some shear in the elements in the y direction because of the torsional moment, even though the load is acting in the x direction. The equation is this one, again very similar to mc over I equation. However, in this equation, we consider the sign, whether it is negative or positive. We still consider those because these are in opposite directions, and they add up to zero as a total, and is demonstrated now in here. When you look at this very closely, those shear forces that are shown in circle are the ones that are developed in those elements that are in y direction. So even though the force is acting in the x direction, still there will be some shear forces developed for the elements that are in the y direction. Now, if the force applies in the y direction, pretty much the same thing happens, but in a different direction. Again, we have the accidental eccentricity to be considered and added to the theoretical eccentricity. Our theoretical eccentricity is Ex, and perpendicular to the direction of the force, the dimension is A, therefore 5% of that is considered. The total shear is made of two components in each element. Vyi is a direct shear, Vyit, Yiv is a direct shear, Vyit is the one because of the torsional moment. Torsional moment in this case is called Ty. Equations are very similar. Direct shear, additional shear because of torsion, and again, don't forget that if this term for the force, for the shear in the direction of the applied force, if it is negative, then we use 0. So it cannot be deducted from the direct shear. All right? The distribution of shear forces when the force in the y direction is shown in here in this figure. Again, notice that the equivalent effect of Fy at the center of mass, so as shown in here, is an equal force Fy and the torsional moment Ty applied to the center of the rigidity. The distribution of forces shown in here, Vy1, Vy2, Vy3 are because of the direct effect of shear. Some of those will have additional shear because of torsion. And just like before, the load in the y direction also creates some shear in the elements in the x direction because of the torsional moment, even though the load is acting in the y direction. And how do we find that shear force? Here is the equation. Again, in this case, it could be plus or minus. And note that the correct sign that must be used in the dimensions xi and yi when an element is below or to left of the reference point, the sign is negative. It is important you carry the negative sign throughout the calculations. A few observations. 1. In the equations for the center of rigidity and distribution of lateral force, we can use relative values for rigidities. For example, if Rx1 is 1,000 pounds per foot and Rx2 is 1,500 pounds per foot, we can simply use Rx1 equal to 1 and Rx2 equal to 1.5 and so on. Notice that because of the accidental eccentricity requirement, in cases where the center of rigidity and the center of mass of the structure coincide, we must still consider minimum eccentricity equal to 5% of the dimension perpendicular to the lateral force direction. This will always result in a minimum torsional moment. 3. Again, we emphasize that in the direction of the applied load, the shear effect because of the torsional moment cannot be deducted from the direct shear applied on the elements. Number 4, in situations when a lateral load resisting element, example is shear wall, is inclined, the procedure is to use the relationship between the local axis of the element to the global axis and resolve the element into two components that are parallel to the global x and y axis. Let's demonstrate this. So here we have an element which has a rigidity of r, its local axes are x and y, and it has an angle theta with respect to the global axis. Considering the fact that generally the lateral load analysis is done separately in the x and y directions, and also considering the rigidity R being in the local x only, it can be shown that R is resolved into two perpendicular components in the global x and y axis. These would be Rx and Ry. In other words, we are resolving R into two separate elements which are perpendicular to each other. Now, the explanation here says that R is only in the x direction. There is no rigidity in the y direction. Therefore, as you know, when we transfer a coordinate system to another one, we have a 2 by 2 matrix. However, in this case, because there is no component in the y direction, the equations have become fairly simple. Rx is R cosine squared theta, Ry is R sine squared theta. Let's look at some examples. In this example, we are considering a force in the x direction for the floor plan configuration shown. Now we have on the north wall or north frame, we have rigidity equal to R. In the south, we have rigidity equal to 1.5 R. So there is some unsymmetrical condition. Parallel to the y-axis on the east, we have a element with rigidity R. On the west, on the west we have R. On the east we also have R. And then somewhere in the middle we have another one, and is also unsymmetric, as you can see in this direction. Distances are shown. For example, for Rx1, it is at 45 feet from the reference point, and Rx2 is at negative 45 feet, and so on. We have also the distances for those elements in the y direction. All right, so now let's see how this problem is done. The total dimensions are 90 feet and 120 feet. We put the force in the x direction and figure out what would be the shear forces developed in the elements. So here is a summary of our rigidities. And we are assuming the mass is distributed identically in each floor. And the weight of the walls and the floors are all symmetric with respect to both x and y axis. All right. Therefore, the center of the mass is the same as the geometrical center in this case. So x bar is equal to y bar is equal to 0. Now, considering the coordinate system, the distances of the north and south elements from the reference axis are 45 feet and negative 45 feet, as we talked about them. And for the east and west elements and the middle one, again, one of them has a positive x, the other two have negative. All right, so let's just plug them in the equations. We want to find the location of the center of rigidity, y, r. Notice that we have carried the negative sign. We get a negative 9 feet. So what does it mean? The negative sign indicates that this location is below the geometrical center. Therefore, the eccentricity from our equation is y bar minus yr. Y bar was 0, and that's the eccentricity theoretical. All right, so what's the eccentricity we use? Theoretical plus 5% of the dimension which is perpendicular to the direction of the force. So we have 9 already, 5% of 90, which is the dimension, we get 13.5 feet. Therefore, the torsional moment is Tx, which is 13.5 multiplied by Fx. Now, the location of the center of rigidity in the x direction obtained similarly with consideration for the negative signs. Don't forget that. So you get negative 6.67 feet. Negative sign means the center of rigidity is located to the left of the geometrical center of the floor plan. Now in this case, the theoretical eccentricity is 6.67 feet. and make sure to add the 5% additional if you are doing the calculation for the force in the y direction. But in this case, we just do the calculation in the x direction. All right, these are the equations again for the total shear, one from the direct shear, the other one from the torsional effect, and the equations we talked about before are here. And don't forget, if this term is negative, we use 0. And for the east and west elements perpendicular to the direction of the applied force, remember that we still have some shear force developed in them, even though the force is in the x direction. Okay, so plugging numbers in them now. First, we find the term that I call it the rigidity inertia. Remember the denominator of the term that we had in there is sigma rxi yi minus yr squared plus sigma ryi times xi minus xr squared, and that turns out to be equal to this value. We also find some of the rigidities. Now we are looking at the elements which are parallel to the x-axis. We had 1 on the north, 1.5 in the south. All right. So for the direct shear, for the north element, rigidity was 1 divided by total rigidity, so we get 0.4 fx. Torsional effect, we have this term, we plug it in there. And at the top, we have the rigidity of the north element multiplies corresponding distance from the center of rigidity. Now notice that the negative sign was put in there and turned out to be positive. So carry the negative sign throughout the calculations. So we get an additional 6% of fx because of shear, and it's positive. So it would be added, and therefore we'll have the total shear in the north element as 0.46 fx. For the south element, the direct shear is according to its rigidity. Rigidity was 1.5, so we get 0.6 fx. But notice that when we put the values in the equation for the torsional effect, we get a negative value, which is of course less than 0, so we do not consider this term. And as a result, for the south element, the shear is 0.6 fx that we computed already. All right, now in the east and west direction, the effect is only because of the torsional moment. So again, that's the equation. We'll plug the numbers in there. And depending upon how these elements are situated, we get 3 values because there were 3 elements. So for each one, we put the corresponding values for their distances. We are not forgetting their signs, and remember the denominator we computed in a couple of slides earlier. So these are the values. See, some of those are positive, some of those are negative. We still keep the negative sign because in this case we don't have any direct shear. All right, and the sign really doesn't mean much, but we can still show them on your figure to see whether they are in forces going in the north direction or south direction. But nevertheless, notice that the sum of these forces, these 3 forces, would be equal to 0. They maintain the equilibrium. So let's put everything together, and this is what we have right now as part of the final results. As you can see here, for the north element, 0.46, these are all fractions of fx. South is 0.6. Now sometimes people ask why this 0.6 plus this 0.46 does not add up to 1. Because of the shear effect and because the code doesn't allow us to deduct the shear from this value. Now in the y direction, remember we got 3 forces. We are showing them in here. A small amount. Nevertheless, there is a shear force developed. And also notice that we put the force at the center of the mass, rather at the center of rigidity, and then apply the moment in there. The eccentricities are also shown. EY is equal to 9 feet, EX is equal to 6.67. But again, these are theoretical values. Remember, in reality, we added those 5%. Okay? Percentages. All right, now this is another example. We want to compute the center of mass and the center of rigidity for a typical plan shown in here. Now here we have the information. The walls are 12 feet high on each side, on all sides actually. The wall density is 75 pounds per square foot on the south wall here, 25 pounds per square foot on the north wall because there are glasses and openings and so on. The east and west walls each has a density of 55 pounds per square foot. So there is a wall here, there is a wall there. The rigidities are symmetric, walls are symmetric, so it looks like that in the other direction, in the y direction. When we do the calculations, we will see that there are some symmetry in there. The total weight of the floor is 42.5 pounds per square foot. All right, so that's the dead load of the floor. And we want to also find the shear developed in all these elements when we have a force applied in the x direction. So when we get a force applied in the x direction, we want to figure out that what would be the shear values. Now dimensions are 45 feet perpendicular to the x direction, 65 feet perpendicular to the y direction. All right. So computing the center of mass, let's do the weight calculations. We divide the entire thing into segments, as I told you about. So north wall, south wall, and floor. So we have 3 segments. And also south wall, east wall and west wall. So we have 5 segments, right, altogether. North wall, 65 is a dimension, is a length. 12, remember, 6 feet from the upper floor, 6 feet lower floor, half of the height from top, half of height from bottom, so it's 12. Density is 25. I divide the whole thing by 1,000, so I have in kips, 19.5 kips. What's the distance to the center? 45 divided by 2 is 22.5. South wall. Length is 65. Corresponding height is 12. But then the density is higher, 75. So you get 58.5. Negative 22.5 feet, right? Because it's below the reference point. Now, east and west wall each, they are same as far as the configuration is concerned. 45 feet is the length, 12 height, 55 density, divided by 1,000, 29.7 each. However, one of them has a distance equal to positive 32.5, the other one has a negative 32.5. So keep that in mind. Okay, now let's continue. It's a good idea to show these things in the table, but we have not forgotten the weight of the floor. 42.5 density, total size 45 by 65, and again divided by 1,000, you get 124.3. So what are the distances? The center of gravity is right at the center of geometry, so there is no distance in that. Distances are 0. So I want to put this in a table for clarity. So here is a table. In the first column, call it segment, north wall, south wall, east wall, west wall, floor, and summation. Do the weights, write all the weights we computed, corresponding distances, and do this product. So you notice that some of these distances are numerically the same, but they have different signs, but carry it out throughout the calculation. Some of these terms will compensate each other, right? But they still write them so you won't make a mistake. So algebraic sum for W times Y prime, sum for the weight, divide this value by this, and there you go. You get Y bar, that's the location of the center of mass. Negative value, so that means we are actually below the reference line, right? How about in the x direction? Remember, everything was symmetric. So continuing the calculations for the center of rigidity, these are the equations that we discussed earlier. Again, the best thing is to put a table together. So I put a table. Here I have a segment. So what does it mean by segment? That means which resisting element. So north element, south element. We only have two, right? We have only two in the x direction. One has a rigidity of 1, the other 5. One has 22.5 feet from the center, the other negative 22.5. And do the product. All right, algebraic sum and sum of the rigidities. Take this one and divide it by that. There you go. You get the location of the rigidity in the y direction as in negative 15 feet. How about in the x direction? Rigidities are symmetric, and as such the location of center of rigidity xr is equal to 0. Alright, so now let's compute the shear forces. First, the theoretical rigidity. We are looking in the forces in the x direction. So eccentricity theoretical is Ey. Y bar minus YR. We have the two calculated. We are carrying the sign, so we get 11.65. Torsional moment now with the 5% accidental eccentricity considered is 13.9 Fx. And for the north and south element, parallel to the direction of the applied force, you get the summation of the two terms as we talked about, and these are the equations, so I'm not going to go over them, and we'll just plug numbers. But let's first find this denominator. This is the calculation that we do. This is the calculation for that denominator, and on the north element, rigidity was 1. Total rigidity is 6, so we are talking about 17% of Fx. That's the direct shear. Torsion effect, now take this value and plug it in there. Rigidity is 1, distance is 22.5 plus 15. We're talking about the distance to the center of rigidity. The torsional moment 13.9 Fx, so you get an additional 0.07x, which is positive, right? So you add it. Therefore, you get a total shear as 0.24 Fx. How about the south element? Rigidity is much higher, so we ended up with much higher shear force. However, when we put the effect of a torsion, it turns out to be negative, therefore it's not considered. So we simply use whatever value you had in there as our shear force. Now, of course, the force in the x direction would still have some effect on the east and west elements. So those are according to, again, our MC over I similar equation, right? So denominator, remember that from previous calculations. Corresponding rigidities, corresponding distances with the sign carried out. The total moment is a moment created by Fx. So one is a negative 0.065 Fx, the other one is positive. Always some of these would end up with 0. And there we go. A summary of all the forces are shown. North 0.24, south 0.83 Fx. And then, of course, east is 0.65, west is 0.65. And these are only when the force is acting in the x direction. And you can carry the same calculation if the force is in the y direction. All right? Now, how do we compute the rigidity? We talked about rigidity being R, but in this part of the lecture, let's talk about how to compute the rigidities. The rigidity R, which is also called the lateral stiffness, is computed by applying a unit load on the top of the frame or shear wall and computing the corresponding displacement delta. And then the rigidity is simply 1 divided by delta. The unit is kips per foot or pounds per foot, as you saw in my example. Generally, a shear wall or frame is treated as a cantilever system free to move at the top and fixed at the bottom. A brace frame can be idealized as a truss. Now, these are when we want to do hand calculations. However, there are certain cases for which the frame or shear wall can be considered as restrained at the top against rotation and only allowed to move laterally. This can be the situation when the beam or the beams in the frame are considered very rigid, or they are much higher in terms of the stiffness compared to the columns. All right, so let's just look at some examples. We'll look at some examples later. The lateral deflection for these two situations would be different. So depending upon how you idealize, make sure to use the correct equations. All right, so in the case of brace frames, and for the sake of simplicity, we may assume that braces are the only elements resisting the lateral forces. In other words, the beams and columns remain rigid, and we are also considering that the bottom connections are like hinges. So here you see a steel frame, and we are assuming that the columns and beams are rigid. So pretty much there is a rigid body motion for those elements. Any deformation is because of these braces. And top deflection is delta for the force 1 kip, for example. All right. Now for shear walls, we have two kinds of idealization, as I said before. Cantilever idealization and top restraint against rotation idealization. So you can see that if I show you the single column, how the deformation would appear. And I'll give you the equations for both these cases. Now for a moment frame, two idealization again are considered idealizations. One is a cantilever idealization like before. The other one is top restraint against rotation, this one. And then these idealizations are important in simplifying the process, and we can do hand calculations. So let's look at a brace frame. We can do hand calculations, and I demonstrate this through an example. So let's look at this example. We are talking about a 5-bay frame. Span is 30 feet typical for each bay, and the height is 20 feet. And the bracing is what we call it the K bracing. And this distance A is 1/2 of this 30, right? So it's 15. The elements are HSS 6 by 6 by 1/2 as a cross-sectional area of 9.74, radius of gyration 2.17. So here when we put the load, when we put the unit load in here, we assume that top beams are all rigid, and these braces are the only thing carrying this load and deform. So let's see how we can do the calculation. So the angle alpha that I showed in the previous figure is equal to 53.13 degrees by knowing the geometry. And let's show the free body diagram of the joint, put the unit load in it. One member is in tension, one member is in compression. By knowing the angle alpha, you write the two equations of equilibrium, and you find the tension force in this member. The compression is the same. So tension force is 0.833 kips. Now using Hooke's law, we can find the deformation in that member, knowing that L is the length of the member, which in this case is 25 feet. Modulus of elasticity 29,000 KSI. And therefore, under the force 0.833, this thing is elongated so many inches, 0.00088 inches. But that is not the horizontal deformation of this frame. So how do we compute that? Well, because these deformations are extremely small, before deformation, after deformation, these lines could be considered as parallel to each other. And therefore, we have a little triangle, as you can see here, that this deformation here is delta, and by knowing that the angle is alpha, we can compute capital delta. So capital delta is little delta divided by cosine alpha, and cosine, by the way, alpha is 0.6, and you have therefore the horizontal movement of this frame as 0.00147. So how do I find the rigidity? Just take 1 divided by the delta that you just computed, so that's the rigidity. Now, if you want to have an equation for that configuration, that would be the equation. You can show that, you can write in parameters what the R is, either 2EA. A, remember the A distance, A squared divided by L3, or in terms of the cosine alpha, you can write the equation. Of course, L is the length of the bracing element, and A is its cross-sectional area. Now, a side note in here, the slenderness for the compression member is 138.2. The critical buckling load for that one using Euler's equation is 14.99 KSI. So that's the equation for the critical stress. And if I multiply by the cross-sectional area, I get 146 kips. So if my calculations when I do the design shows that the lateral load is such that this element is stretched beyond this value, then it's going to get into buckling and it becomes ineffective. So we need to increase the size of it. Just a side note. All right, so for eccentric situations, when bracing are like this, in this configuration, I designated the distance as A. Angle still is alpha. We can compute this angle alpha. And actually, the tangent of alpha is h divided by A, and we can get a cosine. And we can show very easily that delta is equal to this value, and 1 divided by delta gives me the R, which is exactly same equation as before. So if you have a panel like this, that's the rigidity for one panel. All right. Now, how about if I have cross bracing like this? Now, there are two situations. When you put the applied load 1, again, to keep the dimensions consistent, I'm using A, but in this case, A becomes like a span length. H is the height, delta horizontal movement. If both bracings are working, in other words, compression bracing is also working, in that case, it's exactly the same equation as before. However, sometimes we consider that the compression bracing has failed. Only the tensile, only the tension bracing works. In that case, as you can see here, the rigidity is 1/2. In other words, this system is more flexible. So it all depends on how you idealize your system. All right, now, if you have a situation like this, when you have several bracing appearing in the frame, so here bay number 1, bay number 3, bay number 5 have the same bracing. The length of each bracing is L. When we put applied load equal to 1, notice that this force is actually divided equally for each panel, for each bay. Is F1, F2, and F3, if they are identical, they are the same. However, the lateral displacement would be the same for all the bays. If it is delta for this one, is delta for this, and is also delta for that. So for each panel, the rigidity is exactly the same equation we found before. So I'm going to call it Ri in the example that I did. All right. Now, therefore, for each panel, if I take the rigidity multiplied by delta, I get the force. And remember that F1, F2, F3, etc. add up to F, which is equal to 1, right? So now I'm going to substitute for each of these F's. You get R1 delta, R2 delta, R3 delta, and The total force, of course, is the total rigidity multiplied by delta. Excuse me. All the deltas cancel out, so we get a very simple equation that the total rigidity, if all the bracing are at the same level, is sum of the rigidities. So for each level, we can find that. All right. And don't forget that if the panels are identical, you just multiply by the total number. So it's much easier, right? And A is a cross-sectional area, A is a modulus of elasticity, and L, don't forget, is the length of the bracing. Okay. Now, how about if the bracings are at different levels and we have a system which is made of several stories? So I have the following procedure for approximate calculations. Number one, compute the approximate RTI for the ith level, right? Just adding all the rigidities for each level. Then you go to next level, do the same thing, next level, do the same thing, and so on. Now, considering the fact that the displacement of each level is 1 over RTI, right? 1 divided by rigidity, and the total displacement is the addition of all these level displacements, then we can show that delta T is equal to delta 1 plus delta 2 plus delta 3 is equal to this. But what is delta T? That's 1 divided by the total rigidity, right? So if I plug that one in the equation, I get this equation. So in other words, if you have a multi-level frame, you simply need to find the rigidity of the entire frame according to this equation. All right. Now let's look at an example. So we use our bracing, the same panel, 3 in this 3-story frame, 3 in the first level, 3 in the second level, and 2 in the third level. So we want to put a unit load in here and get the delta to get the rigidity for this system. But let's use our approximation. Of course, you can use a computer analysis if you wish, but let's use our approximate analysis. So for level, first of all, each of those panels has an R equal to 678 kips per inch. And this was in our previous example. So we know that one. Let's just keep it as R. Then for the first and second level, when we have 3 bracings, that's 3R. For the third level is 2R. Very simple. For the total, remember our equation, plug numbers in there, and total RT is 6R over 7, and put numbers there is 581 kips per inch. Gives you an approximate value that you can use in your hand calculations. Now, what if we have a shear wall? And there are several suggested values as an approximate values. I'm considering the thickness of the wall being equal to T. And remember that we said there are 2 situations. Cantilever one. In this case, we consider the deformation or displacement because of flexure and because of shear. And if it is a cantilever system, the delta is according to this equation. I tell you that the calculations are fairly simple. E is a modulus of elasticity. I is a moment of inertia of the cross section. I tell you what it is. Now, remember this width B, and the thickness is T. So the wall is, thickness is T like that. So that's the wall right there, right this. Okay? And once you get the delta, R is equal to 1 over delta. Now, what if is a situation like that? In other words, the top is sort of restrained from movement. Then in that case, from slope deflection equations, you can show that the portion that corresponds to the bending now is much steeper, right? And the 12 appears in the denominator. The portion for the shear is the same. What is the G value? That's the shear modulus. So what we're going to use for that? A is a cross-sectional area. Let's examine these parameters and find out what they are. Shear modulus approximately for concrete, we can take it as E divided by 2.2. A is a cross-sectional area, which is B times T. I is a moment of inertia, TB cubed divided by 12. For the modulus of elasticity for concrete, 57,000 square root of prime sub c in psi. You put psi in there, you get psi out. So this equation, don't try to use dimensions in it. It doesn't work, right? It's our ACI equations. Now, how about if it's masonry? For the masonry, if the compressive strength is F prime sub m, then modulus of elasticity is shown as EM, which is 900 F prime sub m approximately. G, shear modulus, is taken as 40% of EM with a Poisson ratio of 0.25. So for that, if it is a cantilever system, we can actually show that the equations are simplified like that. You know T the thickness, B is the width, and if the top is restrained, the equations are this. So that's for the masonry. All right, now, what happens if there are openings in the walls, like windows, doors, and things like that? And again, for approximate calculations, we can divide the wall into segments, and then depending upon if the openings are the same level, we can add the rigidities. If the openings are in the different levels, we can use similar to what we had in the bracing frames, 1 over RT equal to 1 over R1, etc. So if all the openings are in the same level is different from if they are in different levels. So in this case, let's look at openings one above each other. In other words, openings are at different levels. And then the total delta is a delta from each level. And here we also consider what we call the rotational effect. When you get the rotation of this, you get an additional displacement, so you need to consider that. And I show you in a figure. And once you have this delta, then R is equal to 1 over delta. And therefore, in this situation, we can simply use that equation for each of these is 1 over R1, 1 over R2, etc. But I'll talk about it later. If wall segments are all in the same level, in other words, you have, let's say, one-story shear wall and there are openings in them, then you can simply add the R's when they are all in the same level. All right, and again, the proof of this is very simple, because if everything is the same level, you get 1 delta for all of this. Okay, so here is some illustration of opening. As you can see, these are sort of vertically, segments are vertically distributed. You get a segment 1, segment 2, there is an opening here, and segment 3, and in this case, you simply add the deltas plus the rotation effect. Here you see the rotation effect. If you have this angle, you multiply by the tangent by the corresponding length, and you come up with how much displacement you get, right? So you need to consider that. And then R is 1 over delta in this case. Here, all of the openings are at the same level. Opening here, opening there. So segment 1, segment 2, segment 3, all the same level. Same delta. And then you can show that in this case, we simply have R as a summation of all the R's. And again, similar to that brace frame I showed you. Okay? How about moment frames? In this case, we apply a unit load and find delta, and we can use a computer analysis. Alternatively, we can use an approximate solution. But again, the two idealized situations, cantilever idealization, top restraints for rotations. All right, in this case, let's just consider displacement when we only have one column. Let's look at one column only. If it is a cantilever idealization, is h cubed divided by 3ei, where h is the height of the column. I modulus of elasticity is, E is a modulus of elasticity. I is the moment of inertia of the cross section. And once we have delta R is 1 over delta, and you know that the corresponding force is R multiplied by delta, right? Rigidity multiplied by displacement. If the top is restrained from rotation, then delta is h cubed divided by 12 VI. And again, R is 1 over delta, and corresponding force is R multiplied by delta. So why do I care about corresponding force? You will see it later. So if there are n columns in the frame, the sum of the total forces, that's what I needed the forces, is R1 delta, R2 delta, R3 delta, etc. Delta is the same if they're all at the same level, right? But remember the total force is equal to 1. So we get R1 plus R2 plus R3 times delta is equal to 1. And sum of the rigidities is 1 over delta. But what is 1 over delta? Is rigidity of the frame, right? So in this case, we have the total rigidity as R1 plus R2 plus R3, etc. If all of these are the same level. All right. Now, if the columns, of course, are identical, if it is a cantilever idealization, is n number of columns multiply 3I over h cubed. And if the top is restrained from movement, is equal to n times 12 EI over h cubed. As an approximate solution, now we have a multi-story frames. What do we do? Very similar procedures as the case of brace frame. First, we compute an approximate RTI for the ith level, assuming a single story following the procedure we just explained. Then, considering the fact that deltas are added to get the maximum delta, we have the following equation for the total delta. And therefore, that means that in order to find the rigidity for the total, 1 over RT, which is total rigidity, is equal to 1 over RT1 plus 1 over RT2, etc. Very similar to case of a brace frame. All right. Well, this is our last example, and we have a frame system, lower level 28 feet height, upper level 16 feet, bays are 36 feet each, elements are given, column size, beam size, etc. All right, so I'm going to do this in parametric, in terms of parameters rather, like a parametric study first. So in the first level, we have 2 columns. So if the rigidity of one column in the first level is R, then we get 2 R's, right, for the first level. And R, considering the top is restrained, that would be the situation here, right? And considering that the rigidity of beams are into the calculations and consider they are more rigid. So we can use that idealization that R is 12 VI over H1. That's the height of the first level, right? So we call that one as R. For the second level, rather than doing numerical calculations, let's find out what is the rigidity in terms of R. So the ratio of the two heights is obtained. So that means the height for level 2 is 0.571 times height of the level 1. And as a result, right, we would have R prime, if we call it the rigidity for the column in the second level. You can show through the calculation that that is 5.371 times R. So now everything is in terms of R. All right. Then we can, at the end, we can put numbers in there. And for the second level, we have 2 columns. So, right, so RT2 would be equal to 2 R prime, right? And then each R prime is equal to this value. So now we have, in terms of the R, RT2 as 10.742 R. Okay? Now we'll go up first level, second level, add it using our equation 1 over RT1 plus 1 over RT2, plug numbers in there, and solve the RT, which is equal to this value. And now I plug numbers. And I come up with the rigidity of this frame as 8.08 kips per inch. That's for R, right? Not for the frame. So that's for just one R. For the frame, as you remember, is equal to this value. Therefore, I need to multiply R by 1.686. For the entire frame is equal to 13.63. So for one column is this much for the first level. For the entire frame is this much. Approximate calculation for rigidity of a frame system. This video is intended to provide simple computations for finding the rigidities of lateral load resisting elements in wind and earthquake analysis. Furthermore, the procedure on how a lateral load is distributed to such elements as shear walls, brace, and moment frames is explained. In cases where a combination of two types of lateral load resisting elements is used, the system is called a hybrid system. There are rules governing a minimum amount of force that each element must resist. Please consult with the pertinent design code to understand the requirement for hybrid systems. Thank you for watching this video.